So, hi everyone, welcome to the ML Workshop series 2 out of 4. Today we'll be going over the convolutional neural networks. So joined by me is Edward Yan from ACM AI, and I'm from Triton Neurotech, and together we will be present to you today's material. So just to kind of give you like a run through of the workshop series and like the future of the workshop. So we have gone over deep neural network in the last workshop. Today we're going to go over CNN. Then we're going to go over BNN, which has the power to let the model say it's not sure when it is not sure on the data it is training on or doing inference on. And finally, we're going to go over one of the most, breakthrough models in natural language processing and image classification, which is transformer. So what are we going to cover today? Today, we're going to have a quick, brief recap of DNN and TensorFlow, and we're going to just briefly kind of go over the backbone of practical implementation details of ML model in TensorFlow. We're going to, again, briefly go over the baby data set. And Edward is going to present on every single fundamental component of a convolutional neural network, as well as data augmentation, which is a practical way to even make the performance of CNN even better. Then we're going to use some transfer learning technique to let you use state-of-the-art models out of the box for your own application purposes. So I'm going to stay on this screen for like 10 seconds. So if you're interested in either joining Triton Neurotech or ACM, please take a screenshot right now. And then after 10 seconds, I'm going to move on to today's presentation. All right, so let's get started. So again, today our agenda is we're going to go over neural networks, CNN, data augmentation, and transfer learning. If you want to have a quick recap or to look at last week's notebook, you can go to the link here. And we also have the recording on YouTube on this link here. Let's just briefly recap on what linear regression is. So here, the idea of any machine learning model can be think of finding the line of best fit. Here we see that we have some data. Here the blue dots are data. It has the value X and we're trying to predict its value Y. And our goal is to trying to find a line of best fit that will minimize the residual. And the residual are the sum of the difference between each point and the line of best fit. And we take the square residuals for our purpose here. You can technically take the absolute values of the sum of the residual, or you can take the square residual. As the square residual is being used more often for purpose we won't go into in this workshop. So if we look at the graph of originally when our model is on train, we have like a large sum of square residual. But as the model progresses, we can see that we start finding the line of best fit throughout the training of the model, and we're going to put it in concrete terms now. But here, the goal or the terminology that we use is the square residual is actually, let's define it as our loss function. So we learn a parameter. So here we're learning two parameters, the slope and the intercept, or beta and alpha. And we're going to get our y hat, which is our predicted y value. And our total loss is literally just the square residual over every single data point. And we have a normalizing constant 1/n. So yeah, here is visualizing the square residuals. So here, let's say in the 1D case, we're trying to find we only trying to find alpha or the slope. Then our loss function versus parameter graph will look like this. We have the loss here, we have the parameter. And if from the calculus or analytical perspective, you can simply take the derivative when the loss equal to 0 and analytically solve for the alpha that will minimize the loss. But this might not be possible when the dimension of the parameter is high. So what people do is we do something, or the core bone of machine learning, which is called gradient descent. And the gradient descent is we take one little step at a time until we reach the local or global minimum, depending on the context. And how many steps we take is the number of epoch we define. If we take too few epoch, we're not gonna get there. So we have to, take enough epochs. And how big? So if you look at here, each arrow we take some, we take certain, certain step size toward the minimum, and how big of that step we take is scaled by the learning rate. So you might be thinking, so how do we know what's the right learning rate? So if you look at the graph here, if we take small step, our model is gonna take forever to reach the minimum. If we take the right step, we're gonna reach your minimum in not a lot of time. But if our learning rate is too high, we're going to overshoot, leading to divergence of a problem. So there's something called hyperparameter tuning, which every machine learning practitioner would use some research approach or base-off approach, or just manually tuning the right learning rate for the problem we are doing. So just to literally contextualize the entire vanilla algorithm, so you will know, exactly what's going on behind the scene. Here, T is the number of epoch we take. So T equal to 0 is like one of those little steps right here. T equal to N is like our final step right here. And every single time we're going to update our parameter W. W can be collection of all the parameter from intercept, slope in the 1D case, but it can be more in the high dimensional case. And it will go opposite the direction of the gradients. Want more details, you can revert to the last workshop or refer to the visualization above. So here we're going to implement everything in TensorFlow. So here, first thing we do is we have to create a model. The model will be covered in just a bit. So just think of it as a black box for now. We're going to define our optimizer, which is our gradient descent optimizer. Again, if you want more information, please refer to the last workshop. And the loss function that we use here is the mean square error, as described earlier. So now what happened is we're going to get the y hat. So here the model, just think of it as a black box. We give it some input x. We're going to get a value y hat, and we're going to calculate the loss values of our mean square error loss given y and y hat. And then we're going to calculate the gradient. So why do we want to calculate a gradient? Because gradient is the gradient J term here. That's why we're calculating the gradient. And we're going to apply the gradient. So when we apply the gradient, we pretty much perform this function right here. And then, yeah, that's pretty much it. And I'm just printing the loss at every single epoch for us to see. So we can see that the loss value of every single epoch just reduce, as the number of epoch increases. So that might be a lot of code, and you probably know this, very well, and you don't want to implement this whole thing. You can do the exact same thing or the equivalent code of above by using model.fit. So here you use this two lines to create a model. You compile the model and you do the model.fit. But you might want to use model.fit, or what we did above is called a custom training loop, depending on the purpose of your problem. So one more thing we want to cover before DNN architecture is overfitting and underfitting. So here we have some data. We're trying to find, the line of best fit. And we see that here we have the optimum fit, and here our model is underfitting, which means, it's not fitting the data at all. And overfitting means we're overfitting the data such that our model does not generalize well to new data. So you might be thinking, okay, visually we kind of can tell what overfitting, underfitting, optimal is, but is there like a strategy that we can detect overfitting, underfitting more systematically? And there is, and that is actually called the training testing split. And some people do training test split, some people do train val test split. the golden standard is to do the train file test split. So that's what we're going to implement in this notebook. So the idea of training validation test split is we split the data into this 3 portion. We train our data we train our model only on the training set. And we're going to look at how our model performed on the validation set, which the model has not seen before in its training. And once we see that, the model performed both well on training and validation, we're going to test our model's performance on the testing set. And if it's good on the testing set, that means that our model is ready for production and to be used by consumers. And just one thing here, if the training and accuracy is higher than validation accuracy, then that means our model is overfitting. If training accuracy and validation accuracy are both high, we have found an optimal model. And if the training accuracy and validation accuracy are both low, then our model is underfitting. That's how you know how your model is doing. So last thing we're going to cover before CNN is briefly, we're just going to review on DNN architecture. So a DNN consists of an input layer, some hidden layers, and output layers. So what activation function is, so at every single layers, we pretty much have an output equal to some weights times our input X plus bias. And we're simply going to wrap around a G function after Y to add some nonlinearity to let our model to learn more complex functions. And what G function to use, it turned out the most universal function that people use is the ReLU function, which is simply, if the value is negative, it's going to be 0. If it's positive, then it's just going to be an identical mapping. If you want to have more intuition on activation function and ReLU, please refer to the last workshop. The last thing we're going to cover is the number of neurons and layers. So here we can see that we have a single layer with 1 hidden unit. Practically speaking, we can have more neurons in a single layer, and we can also have more layers. When we have more layers and more neurons, our model is more prone to overfitting. When we don't have a lot of neurons and we don't have a lot of layers, our model is more prone to underfitting. And we do trial and error, or we do some hyperparameter tuning. And the hyperparameter in this case is number of layer and number of hidden units. We're going to find the optimal solution or optimal model architecture for our purposes. So here is how do you implement a DNN in code. So here we just create a sequential instances. So in TensorFlow, there's the sequential model, subclassing model, functional model. The simplest being sequential model. So I just illustrated here. And we can simply add the input layer and specify the shape of the inputs. And in this case, the input is just the height of person. So the input dimension equal to 1. And we have 3 hidden units. So that's why I'm going to add a dense layer with 3 hidden units. And after the hidden units, I'm going to follow up with a ReLU function. I'm going to do it for layer 3 and layer 4. And finally, the output is the weight of person. So I'm simply adding a dense layer with 1 hidden unit. So that is pretty much, a brief review of DNN. So now we're just going to let you look at the baby data set, which we go over last time. So we given the images of the baby, we try to predict its height. And this image to height matching come from certain underlying distribution. And our model's goal is trying to find this underlying distribution transformation from image to height. And with the DNN that we just covered, we were able to get a mean square error of 813 on the testing data set. And now we're going to introduce how we can improve this mean square error on the test loss. So we're going to see a lower value by using CNN. So Edward, whenever you're ready, take it away.
So as Michael mentioned, we want to motivate this section first by talking about how we can effectively get how we can get performance improvements from this baby data, from this baby net, while also using less parameters than BabyNet. And so this is our segue into convolutional neural networks. So convolutional neural networks fundamentally is just a lot of like convolutional layers combined together. And so we want to just start off by discussing how they work and potentially implement some of them ourselves. And so this is just like kind of like a short demo of how convolution works. And I'll just play it a little bit. So the kind of like most important part of a convolutional layer is the idea of a filter. What a filter is, it's the trainable part of a convolutional layer where, as you can see, each of these, like the 0.6, 0.2, 0.5, these are the weights of said filter, which are trained during the training time of our deep neural network. And how these filters are applied to the input, which in this case is the matrix, is that given like associated, like let's suppose like the first indices, which is the 0.6, this is then applied to the 3 and so on and so forth. So and then basically you multiply this whole filter with this section of the matrix, and then combining these two will get the end result, which is going to be the output from this convolutional layer. We will basically, first of all, this is the PyTorch equivalent of this network, of this convolutional layer, which effectively is a filter that's 2 by 3, and the input can be any arbitrary size with the result of a 2 by 2 output. And so we can just start off by kind of like implementing the convolution we see above. The main thing you want to know about a convolution is this idea of multiplying each of these elements with the corresponding elements in the matrix. So if we just continue going over this simulation, we see that this filter is applied to every 2 by 3 chunk in this input matrix, which then corresponds to one specific element in the result. And how to implement that in code is just to nested for loops. This is a very inefficient method in NumPy and also in PyTorch and TensorFlow. There are much more efficient ways to do this, but this is the most intuitive way to demonstrate how that works, where we iterate through the range of the kernel first, which in this case is going to be 2 by 3. And then for that, we first iterate through, oh my bad. We first iterate through the kernel, the image, and then based on that, we iterate through the kernel itself. So this is kind of like just like the dot product of each of these elements together, which generates the end result, which is going to be an output. However, we want to add that, what if we don't want to slide over each individual element? Because like we can see that in this one, it manually slides this filter across every single element. And this is not ideal in most cases because, well, what if we want to not have to use this 5 twice? What if we only want to use it like once? And to do that, we would be using strides. So what a stride is that instead of sliding over each index manually inside the input image, we instead opt to kind of like skip a term, if that makes sense. Skip a term for our kernel for every single time we apply the kernel. And to implement stride, it's pretty simple, where we split the input image basically as a sort of like pattern. So instead of like a 0, 1, 2, 3 input, it becomes like 0, 2, 4. And that's effectively how we implement a stride. However, we have to also ask ourselves, based on this like non-1 stride, like if it's like 2 or 3, there could be a potential of some elements in the image not having the kernel applied to them. And so to handle this problem, we also introduced the idea of a padding. So what padding is that effectively, instead of just treating this input as this, we also add like a sort of like zeros around this input. And by doing this, the kernel is able to physically apply to each individual one more effectively. And the TLDR is that striding kernel lets us apply like iterate faster through the whole input, while also just covering everything. But then we also have to ask ourselves, what if we want to iterate through the kernel without having to actually change the stride or the size of the kernel? And if we want to do this, we would be using a dilation. So what a dilation is, as you can see in this diagram, is that instead of this original 3 by 3 kernel, which we most commonly understand, we can use something like a expanded with a dilation factor of 2 kernel, And so this is like, so each element in this kernel corresponds to an associated element here. So this corresponds to this one, this corresponds to this one. And by doing this, we have a much larger coverage of the overall image, while also being able to iterate through the image much faster. The benefits of this are that it has relatively the same amount of performance, but you're able to process and handle the overarching image at a much faster pace. And to implement that, it's a little bit more complex in the implementation. We would just add like a dilation. We would first dilate the kernel, and then we can directly apply the dilated kernel back into the image by treating it as the original kernel. If you have any questions about these implementations, or if you want to implement the convolutions yourself and test these out, I have put the link to the notebook inside the chat. Yeah, and then based on these values, we can effectively calculate a formula that computes the output dimensions given the input dimensions of the image. And so this is the formula. I'll give you guys like a moment or two just to understand each of the components. Effectively, we take padding, dilation, kernel, and stride, which we've covered before. And using these factors and using this formula, we're able to calculate the corresponding height and also width of the output image. Does anyone have any questions up to this point? Okay, so I guess if there's no questions, I can just continue. So another cool thing is that there are specific kernels that do specific things. And what I mean by this is that if you want to just like implement a kernel yourself, you can also have, instead of like training the kernel to identify specific things, there are some preset kernels that people have discovered that do pretty cool things. So first is the identity kernel. What the identity kernel does is that it gives an exact output of the input. And this is the corresponding kernel. And there's also edge detection, which will detect the edges of the image, which looks like this. There's also sharpen and also blur and Gaussian. There's also Gaussian blur, which can be something like this. The main gist I want to get across is that there are a lot of different kernels that you can do for a lot of different things, and that the purpose of convolution of a convolutional layer is to effectively apply some sort of arbitrary kernel such that it creates a meaningful output that can later be interpreted by the network to mean a certain thing, if that makes sense. Kind of like the purpose of a lot of convolutional layers is to extract relevant features from the input image. And this can be done through like edge detection or blurring the image. So apart from applying these kernels to an image, there are also some pooling layers. And the idea of a pooling layer is that instead of applying the kernel, instead of having weights for this kernel, we can just directly determine some preset function that we can apply to said function. In this case, this is the max pool layer, which what this does is that given this input 2x2, I want to say filter, it finds the maximum of these 4 values, which is in this case going to be 8, and this outputs this into the result. The purpose of like max pooling and average pooling layers is that they basically decrease the size of the input in a much more apparent manner, while also extracting the most important features in the network. So kind of like how I want you to imagine it is that, are we able to use like identity, edge detection, or any of these kernels to find the maximum value inside an image? And the answer would just be like, no, it'd be very difficult because sometimes the input, the maximum is at this index, or sometimes it's at the bottom left or bottom right. And because it's at a different location, it's going to be really hard for you to implement a preset kernel or a set of kernels to always detect the max. And so because of that, using stuff like max pool and average pooling is a much more efficient manner to go about doing so. So basically, if you want to consider max pooling with relation to like regular convolution layers can turn the input into some sort of relevant representation such that they can be applied to like max pooling to be interpreted further. Basically, it's like a lot of like chain of making the interpretation much more easy to understand for the model itself, and to just extract only the most important information. I guess in the context of what we're doing right now, in the context of the baby's data set, it would be kind of extracting like the height, like arbitrarily, I'm not really sure, but it can extract like sort of like the top of the baby versus the bottom of the baby. And based on this, it's able to figure out the height. Or even better, it's able to extract like how long the legs are with relation to the top. And based on like these type of values, it's able to predict how high the baby is. Does anyone have any questions up to this point? Michael, do you want to add anything?
Yeah, I just want to, I think Edward, you will cover this in just a second. The one thing you guys, and Edward, do you mind going back to the convolution animation?
Mhm.
So if you guys look at here, like the matrix is simply a 2D matrix. You can think of it as our data, our image data, which has width and height. And the filter is effectively the weights, our model is going to learn. So you can imagine that, our model, if we stack a lot of layers together, we're going to have a lot of different parameters, right? Because let me just, I'm able to annotate. Let me just annotate here. Let's say, originally our matrix is 3x4, right? And then we're going to have some kernel, and in this case, the kernel's size is 2x3. And then the final output of our matrix also depends on our stride size, like both vertically and horizontally. But here we only taking the stride size of 1 horizontally and stride size of 1 vertically. So our output shape is going to be 2x2, right? So what we eventually do is that we're going to flatten this this output shape into a 1D array. So here is 2x2. We can simply just Trevor, I'll answer your question in just a bit. But eventually we'll flatten our array. And then you remember earlier when I was talking about DNN, we can just simply start building DNN once we have flattened this array. But you can imagine this can be like we can have a lot of parameters, right? Because if our matrix is big, we'll have just tons of parameter. And what Edward was saying is we can use a max pooling layer. So when the max pooling layer was first invented, of course, it was able to capture the invariance of the image, like Edward was talking about. But another big advantage of max pooling layer is it doesn't have any parameter. It is simply a max function. So let's say we have a 4x4 4x4 just matrix at the somewhere in our model, and we can simply take a max pooling filter with a step size of 2 vertically and horizontally. So it's going to take the max values of these 4 boxes right here. It's going to take a stride size of 2 left rightward, and it's going to take the max of this value, and then it's going to take step size of 2 downward, and it's going to take the max value of this 4 boxes, and it's going to take the stride size of 2 rightward. So eventually our outputs will only be 2x2 instead of 4x4. And this transformation has no parameter because it is simply a max function. Unlike convolution, where we actually have to learn, the weights to multiply by to get the resulting matrix. So by using max pooling, not only we capture the spatial or the invariance of the image Edward was talking about, it also cut down on the number of parameter of the model significantly, which can result in faster training. If you think about images, you have like 1K HD images, that's like 1,000 by 1000 by 3, and how big that image is, how many parameter you need. By using max pooling, you're really cutting down the number of parameter and also capturing, salient features. So Edward, if you can answer Trevor's question and continue, that would be great.
Yeah, I answered his question in the chat. Okay, so I guess moving on from what Michael said, we also have a demonstration of some of the, first we'll kind of demonstrate our implementation of a convolutional layer and then compare it with the actual implementation from TensorFlow. So first we want to kind of like execute this one. This is the one with pooling, and we want to just compare our pooling to their pooling. So first, this is our implementation where the input image is just like a set of lines like this. And then this is the output, which kind of makes sense because it takes the first two chunks, or because the kernel size is 2, it takes the first two chunks, and then it kind of like just determines the maximum of the two chunks. And this is just done correspondingly across the whole image to generate this. And this is basically the same as what we get from TensorFlow, using the same sort of implementation. The only part that's a little bit that we haven't explained is this padding equals valid. So TensorFlow uses a different sort of wording than like padding equals 0 or like there is padding or no padding. When they say padding equals valid, it means that there is no padding. But if they say padding equals same, it means that there exists a amount of zeros around the image itself. So that's like the main difference between our implementation and their implementation. But otherwise, they work perfectly the same. Like as you can see in their output versus our output. And now kind of like addressing the other part that what Michael said, we want to first motivate this section by using our own neural network for the baby data set, which has one convolutional layer and also one dense layer. Kind of compare this with the original baby net that we created, which only has, which if I recall correctly, has two dense layers of size 200. And so, as Michael mentioned before, we're able to get similar performance while also maintaining much less parameters, as we can see here, where convolutional BabyNet only has 2.5 mil parameters, whereas the original BabyNet has 3.2 parameters. And once we train it, we can see that, oh yeah, the performance is actually better. So for training models, generally we want to kind of like normalize the input data and potentially also normalize the output data. But for fair comparison, we're not going to be normalizing the output data because initially in this iteration of the baby data set, the input data was not normalized. So you might as well just not normalize it. But generally, it's good practice to normalize everything between 0 and 1, just because neural networks work really well between those two values. The reason behind why neural networks work really well between those values is, as we can see here, kind of like these activations, I think as Michael mentioned before, like ReLU and other activation functions usually have the largest delta between -1 and 1. To kind of like name a few activations, like ReLU is like this, where this is 0, this is, I guess, 1, and this is like -1. And then I think something like sigmoid actually has something similar where this is 0.5 and this is I think 0, and then this is 1. So basically what we can see here is that after 0, the deltas are really small, whereas for sigmoid, the largest delta is basically between 0 and 1. And effectively, if we want to consider this, if we had something like 255, like 255 here, the slope is going to be really minimal. There's going to be little change between like 1 and 255 in terms of the output of that specific network weight. And that's why we want to normalize between 0 and 1. Anyways, that was like a little bit of a tangent. Then we can just like kind of like look at our model. Before we do that, actually, I'll just have this model running in the background because it takes a little bit of time to run. We can see that it takes around 5 seconds to run each iteration. So 5 times 30, that's going to take around like 3 minutes to run. So in the meantime, we could probably like mess around with this sort of visualization for how it works. Specifically, what I want to direct your attention to is the number of dents and also the number. I can do that actually. But I don't think you're allowed to do this while the other one's working. Oh yeah, I think that's why. Okay, yeah, we can do that later actually. Anyways, the next thing we want to motivate is that there are some, let me think. Yeah, okay. So the next thing we want to motivate is sort of like state-of-the-art CNNs. This part is more along the lines of, you don't really need to understand how to specifically implement them, but it's like a good idea to understand the motivations behind why the specific architectures were made in certain ways. The main thing I want to get across is kind of like the evolution of them, how we started off with AlexNet, then we went to BGG, ResNet, and Inception. They also, basically how we know that these are very state-of-the-art models is there is this competition called the ImageNet competition, where I think all of these models competed, and basically as time went on, the model performance just got better, and these are the corresponding models and images of how they worked. The other thing I want to get across is that fundamentally all of these networks use basically the same combination of layers. Like you can see with AlexNet, the most basic one of the four, it only uses convolutions and max pool. A lot of this stuff is a lot of more along lines of experimentation, where they figured out the optimal number of parameters, number of filters to use for each layer. And so they got like pretty good results on ImageNet using this. And this is kind of like the visualization of AlexNet. Moving on, later on, they decided to use BGG, which has like the first sort of important step towards modern neural networks, which is the idea of a convolutional block. And what a convolutional block is, it's two convolutional layers followed by one max pooling layer. And what they did for this is that they found that this is like really effective in getting relevant features. So they just like applied a lot of these together to get like really pseudo results also. And this is like the visualization of what they did. I think the reasoning behind why they created this sort of like representation, I'm not 100% sure off the top of my head why they did this, but experimentally it worked out really well to have like a sort of conv block. And so yeah, and then the next one, this one has like a pretty step forward. It's called ResNet. So what ResNet has, which I really want to get across, is this idea of a skip connection. So what a skip connection right now, or just kind of like a brief recap in comparison of a skip connection versus other ones, is that you see that in a normal network, like this one, everything just goes in one direction. Like each layer, so like if you want to draw this out, it's like each layer, like the convolutional layer is like this one, and then directly the input goes into this one. And then this is like, let's define f as like the convolution function. However, the idea behind a skip connection is that what if we want to apply the function, but also we want to maintain the original image? So kind of like, instead we do something like this, where we directly copy the input, the original input, into the output. So it's kind of like adding the changed value along with the original value. And so this is what a skip connection is. This is very important because this kind of like this is really important when the networks get really deep, just because of the fact that when you get really large networks, they tend to like really forget a lot of stuff, because when you apply a lot of stuff, there's a lot of filters. So a lot of the times, a lot of the relevant information could potentially get lost. And by adding this sort of like skip connection, the ResNet is able to be like, oh, we kind of remember stuff because, well, we directly inputted the input into the output also. So that's like another fundamental addition to like modern computer vision networks. Yeah, so this is like the ResNet. If you want to just like spend a little time looking at it, you can just like use these off the shelf, because a lot of people have implementations of ResNet, VGG, and that kind of stuff. So you can just use whatever you want, like directly off the shelf. So it's not that bad if you just want to just like use it, if that makes sense. And so this is like very complicated stuff. It's like, and this is like the skip connection I was talking about, where each of these like kind of like skips over. And this had like even better performance in VGG and AlexNet on the ImageNet problem. The last one I want to motivate is, is this Inception. So Inception was a kind of more, this is where you kind of get like really funky stuff, where the idea of inception is that you want to just like use less parameters while also maintaining performance. And how they did this is by using like very fine-tuned amounts, like kernel sizes, and also really fine-tuned like values for said kernel sizes, and also filters. Like if you can see here, all the numbers here are really clean numbers, like 256, 1024. They're all like multiples of 2. But then when you get into like inception, they actually use a little bit more complex stuff. They use like, I want to say it's called like half networks or something like that. But the overall gist is that inception performs better. But the reason that it performs better is that there's a lot of like handcrafting involved inside this network for it to work. Yeah. Yeah, like what Vincent said, ResNet has much more consistent in performance. So does anyone have any questions on these three? In the meantime, yeah, we can look at the model itself. Yeah, so yeah, we can look at the model. So we want to first see, when we look at like kind of this like loss graph kind of thing, we want to first like understand how well it's performing, if that makes sense. And in terms of this one, it's going to be the MSC. And what we can see here is that the MSC is actually incredibly low. It's like 99. For context, I think BabyNet was like 800 or something like that. Or yeah, it was like 385. But there's like, yeah, the second thing is like you want to look at overfitting, which it overfits a lot because like, oh, this is like 99. The overall result is like 942. There's like quite a lot of overfitting going on, which will be addressed by someone else later. But the TLDR here is that convolutions work really well because like you're able to get super good performance. Like this is like 100 loss, which is very low when you consider the initial loss was like 1,000 something. So yeah, that's a convolution, and it also takes much less parameters to get to like such a minimal loss with effectively the same amount of training. Yeah. And then the next thing we want to talk about, so that's basically a very short recap of what a convolution is and how to implement your own convolutional layers. But I guess the other thing you want to understand is that our implementation of convolutions is very slow. Like using these like for loops is a very slow operation because you can do a lot, instead of using this, you can do a lot of stuff in like C or CUDA, and those are much more fast implementations. So, and they're also in matrix form. So it's like, yeah, this is like pretty slow, but it's a very good representation of what it's supposed to do. But anyways, does this demo work? Let me run it. And I think it should work now. Okay, yeah. So this is more along the lines of a visualization of the comparison, where we can see that time taken takes like a significantly longer for it to run. Yeah. So it's like you can see the number of parameters required. Like just increasing it to 2 requires 2 mil parameters, whereas the convolutional layer still has 50 parameters. So it's like kind of like as Michael mentioned before, when you use these sort of like convolutions, like these kernels, basically kernels like summarize the data much more effectively than the dense layers. Like if you want to see like a kind of like a drawing representation of it, I'm kind of bad at drawing, but like this is the image, right? This is the image, and then this is the filter, and then the filter becomes this image. So it's like a much smaller portion. Whereas if you want to like, and then if you consider a fully dense network, then it's going to be like something like this, where it's like this, and then like you have like a giant block, right? It's a giant block, and you just multiply this giant block by this to get this smaller image. And if you can just compare this, if we just compare this kernel versus this giant block, you see that this kernel is much smaller than this. So yeah, that is why convolutions are much more efficient. Does that make sense? Yeah, okay. Dude, I'm like really good at drawing, you know? Okay, anyways, the next thing is, this is more along the lines of these two last sections are some of the more stuff that you want to do once you start making your own networks. The first thing you want to do is data augmentation. Generally, what data augmentation does is that it helps your network become much more robust to the input. And what I mean by this is that, I'll do another drawing. I think, yeah, so okay. So let's suppose you have like a person, right? And the objective here is for you to identify this person given a random image. However, you want to realize that this person is not going to always be in the center of this image. Like, what if the input had like the person like at the bottom of the image? Then if your network is only trained on this type of image, it's going to do really badly if the person's at the bottom. And because of this, you want to do a lot of data augmentation, such as cropping, which effectively crops the image, kind of like this, or even like resize, which effectively expands the image, the cropped image, to the original size. And so there's a lot of these augmentations that have the same purpose of just making your network much more robust and given the same amount of input. This is much more important, but you also have to be careful of what you're applying these augmentations to. Like if we look at our original baby data set, like this baby data set, right? It's not really effective for us to apply augmentation to it. Like if you like, I don't know, like crop this image and then resize it, then you don't have a ground truth height for this image anymore because, well, it got expanded. So it's not going to work in all use cases, but generally for computer vision tasks such as segmentation and classification, it works really well because you want to be able to have your network be really robust to the types of input that you can have, like different locations of the input, or even like occluded input and that kind of stuff. And another thing, yeah, so that's basically more along the lines of like a surface level data augmentations, like crop, contrast, that kind of stuff. There are some much more fundamental ones. The one that I really want to like drive home is this idea of Gaussian blur. So let's suppose we have this input image, right? It's like this guy, and then like there's like water here. However, once you apply, but we want to notice is that each of these pixels has a value, such as like, I don't know, like 0, 15, 255 or something like that. Each of these pixels has a value where these values are also, there's a chance that these values themselves are very, like they don't have a large distribution across all the train images. And this distribution could be different from your output images. Like let's suppose in your test one, the input was like, I don't know, like 10, 20, 70 or something like that. And because of these two images having like different pixels, your network doesn't really know what to do with this pixel. Like overall, the image still looks the same. It's still going to be a person like this, but because of this slight pixel contrast, your network might output like a completely different thing. And so that's the motivation behind why you want to use a Gaussian blur and also random contrast. So these are much more low-level augmentations. And what I mean by this is that there are pixel-level augmentations where Gaussian blur effectively blurs this input. So it's like a blurrier version of this guy, but it's not like super blurry in the sense that you can see this blurriness. It's blurry at the pixel level. I mean, like if you blur enough, the picture will be blurred, but like usually you don't blur it that much. And then random contrast changes this, like let's suppose like, I don't know, like a blue arm or something like that. So TLDR is that there's a lot of different augmentation methods, and you should probably experiment along with a lot of these different augmentation methods just to figure out which ones are ideal for your data. And then we can kind of like just show one of these augmentations. In this case, I chose to do crop. And what we can see here is that like given this input, it just like randomly crops out different sections of the input. And then these are then going to be fed into the training, into the model for training. Oh, so it eliminates things like image noise. Well, you kind of want to think of it like this, where you're not eliminating this image noise, you're making your model robust to this image noise. So kind of like in most settings, your training data is like super perfect data. Like it's like really high resolution, and like the targets are also perfect, like they're right in the center. However, this is not always the case in real world applications. Like real world, your camera is probably not like 1080p 720, it's probably like 480 by like 240. And because of that like difference in resolution, your network's gonna struggle a lot because it's gonna be like, why is the image so blurry? And because of that, you want to basically introduce this noise beforehand to your network such that it already understands that, yeah, there can be blurry inputs, but we should understand fundamentally, like you should extract features that are much more important for the network to figure out, oh, this is what a human is or something like that. And in terms of how to deal with varying resolutions of images, you honestly just don't. You want to make your network robust to these resolutions. If you mean like different sizes of images, the most standard approach is to resize it such that all the images are the same size. So like kind of like if your input data is like not like really well made, like you have some images that are this size and some that are this size, you want to resize them such that they're all a standard size. This will hurt the resolution of your image, but then you're able to like actually input into the model. Because if you recall, the input to the models are always predefined sizes. Like this one in ResNet where the predefined size is 126 by 126 with the channel of 1. And because of these like predefined sizes, you can't have your network use like randomly allocated sizes, if that makes sense. Yeah. So that's basically data augmentation, and also you can like add multiple augmentations. So you can like play around with different augmentations. Also, they're like pretty cool stuff, and they help your network be much more robust. Yeah, basically. People with glasses, basically Gaussian blur. Yeah, so that was that thing. And then the last thing I want to kind of show is like, what if you don't actually want to like write out this network? What if you want to use like a pre-trained network? If you want to do that, then transfer learning is the way to go. In this case, I decided to use MobileNet V2, which has already been trained by TensorFlow for you, so you can just directly use it. And the benefit of this is that usually the feature extraction part, all the convolutions in the network, which is like this giant chunk takes the most amount of time to train. Whereas the prediction part, the prediction aspect of it is just like these 2 layers or something like that. And so if you have the feature extraction part already trained, then you can get like pretty good performance without having to spend a lot of time training it, which is the idea behind why you want to sometimes use transfer learning. Yeah. And usually transfer learning has its benefits, which is that you get pretty good results already. And it also has like, but you also have to remember that these networks have already been trained, but the data sets that they're trained on is different from your data set. So you still want to do some like fine-tuning training later on, just so that the data set that you're training on aligns also, your feature extractor understands the parameters or the relevant features inside your data set. Yeah, so that's like another important thing that you have to remember. Yeah. Michael, do you want to add anything?
No, I think we're about time here.
Okay.
Yeah, so guys, thank you for coming to today's workshop. And the workshop in we are currently week 4, so week 6 we're going to be presenting on Bayesian neural network. So I will be presenting on that workshop primarily. So we hope that you can come to that one. It's going to be interesting. So that's everything for today's workshop, and thank you guys for coming again.
Yeah, thank you.